Welcome back. This is our solution to problem 2 from Superquiz 1. And as in Superquiz 1, we're looking at some more what we'll call remedial material. Here we're asked to compute an antiderivative of a function. So just like with differentiation, we're going to be able to find an antiderivative by looking at it term by term. So let me give a name to this function just so I don't have to copy the whole thing down. So how about we'll call this f of x. So if I wanted to compute an antiderivative for f, so this is the antiderivative symbol, then an antiderivative, well, let's see. First we want to hit this first one, and we want to use the power rule. So the power rule tells us that an antiderivative for something in the form x to the n is going to be 1 over n plus 1 times x to the n plus 1, provided n does not equal -1. Of course, if n was equal to -1, then you have this really awful problem where you kick a puppy. We know that in the case where n does equal -1, then you get ln of the absolute value of x. All right, so in this case, we're going to need to divide by 1 more than -5. So 1 more than -5 is -4. And of course this constant just sticks around. So we'll have 2 times 1 over -4 times x to the -4. If you wanted to simplify, you could have -1/2 x to the -4, or even if you like -1 over 2x to the 4th. Right? I don't really care. All right, so now we move over to this next bit, and it actually follows essentially from the power rule. So note when n is -1, right? So if n is -1, then x to the n, right? That looks like x to the -1, which is 1 over x. And this almost is 1 over x. It's just you've composed it with a linear function. So what we'll do here is, well, let's see. We'll start by copying the minus, and we're just going to make a guess that the same rule applies. And we're just going to say that it's going to be a natural log, instead of x, of 1 minus 3x, right? And of course, we keep the absolute values. If we take the derivative to check this, the derivative of a natural log of a function will be 1 over the function. Okay, cool, 1 over 1 minus 3x. And then we have to, of course, multiply by the derivative of that function, right? This is the chain rule. And when we multiply by the derivative of 1 minus 3x, we're going to get a -3. Okay, we don't have a -3 originally, so we need to compensate for that. And the way we can compensate is by dividing by -3 in our solution. So if we divide by -3, okay, we turn this into a plus, and we'll divide by 3. So now if we multiplied this derivative by -3, it would get killed by this 1/3 here, and you'd end up with -1. Okay, so that's how we get the second piece. Let's see, for the third piece, okay, we have a product of functions, and it doesn't look like a substitution is going to be very useful, so maybe we ought to use integration by parts. So you'll call our integration by parts formula, which says if you have an antiderivative of u dv, this is uv minus an antiderivative of v du. All right, so in this case, we're going to let our u be the x squared and our dv be e to the 5x plus 1 dx. Now, I actually am going to assume most people have learned how to use integration by parts before. I just don't like writing all down these u's and dv's. I like using the tabular method. I'll put some links to the tabular method videos in the description. So what I'm going to do here is just write down the two pieces as if they were the u and the dv. And we know with the u's, we're going to be taking derivatives. And I'm just going to keep differentiating until I get down to 0. And then all the other stuff I'm going to be integrating, because that's what you do with the dv, right? Finding an antiderivative. An antiderivative of an exponential like this will just be the exponential, but then by the chain rule, you know if you took the derivative, you'd get an extra factor of 5. So we'll have to divide by a 5 to compensate. And then each time we have to divide by another factor of 5. Okay. And then the way integration by parts works, of course, at each step, you're going to be doing a multiplication. That's what this line is representing, a multiplication. I'll put a plus sign because there's a plus sign there. But then we're going to have to be subtracting another multiplication. Okay, so this is going to get a minus. And then the next time you're subtracting another minus, so this will turn into a plus. All right, and so now we can put this all together. I'll use some parentheses to set it off. We'll have a fifth. And actually, you notice each one of these is going to have an exponential, so I'm just going to leave that out until the very end. So I have a fifth x squared. I have minus 2/25 x, and then plus 2 1/25. And all of that will get multiplied by e to the 5x plus 1. Okay, so there's our integration by parts using the so-called tabular method. Okay, and as you'll see in the other videos, I do have a whole series on using the tabular method for doing integration by parts. This is, of course, the most basic version. It's sort of the simplest version, but we can use it on any integration by parts problem. All right. So next, we have cosine squared of 4x, and I expect I'm going to see probably two different approaches to solving this. One of them using a trigonometric identity, and the other perhaps using, again, integration by parts. So let me show you both methods, just so if you did one or the other, then you'll know if you're doing this correctly. So let's start with, say, the trig identities. We'll scroll down a little bit here, and so an important trig identity to remember is that the cosine of twice an angle is equal to 2 times the cosine squared of that angle minus 1. So in our case, we have cosine squared of 4x. So our angle, right, our theta is 4x. And we can, if we like, multiply this by 2 and subtract 1, and we would then get the cosine of twice our angle. So our angle again is 4x, so this would be 8x. Okay, well, we want to find an antiderivative for cosine squared of 4x, so let's solve for that. So cosine squared of 4x, how would we solve for it? Well, first we would add 1 to both sides, and then we would divide by 2. So this would be 1 plus the cosine of 8x, and then we would divide everything by 2. And so if we wanted to find an antiderivative for cosine squared of 4x, we could instead find an antiderivative for 1 plus the cosine of 8x cut in half. Okay, again, there's this nice 2 on the bottom we can pull outside of the antiderivative, so we'll have a half antiderivative of 1 plus the cosine of 8x. Okay, and the advantage of this form is that it's going to be a lot easier computing an antiderivative for cosine without a power on it, right? Just composed with a linear function. So this will be 1/2. Well, okay, an antiderivative of 1 is going to be x. Okay, an antiderivative for cosine should be sine. So let's say we just guess that the answer is sine of 8x. If we take the derivative, we'll get cosine of 8x times the derivative of 8x, which is 8. Okay, well, we don't have times 8 here, so we're going to have to compensate by including an extra 1/8. Okay, so if we like, we could distribute this through. It's just a matter of taste, really. So we would get a half x plus 1/16 sine of 8x. Okay, but if you left it here, that's perfectly fine. So we come back up, and so this is just off to the side. We can have, oh, of course, there was a minus here, so we'll get a minus 1/2 x plus 1/16 sine of 8x. Okay, now I promised we'll do it with the tabular method as well. So let's head back down. We'll try this again. So we're trying to, again, compute the cosine, the antiderivative of cosine squared of 4x. And so one thing we could do is break this up with our u and our dv, right? The u could be cosine of 4x, and the dv could be cosine of 4x dx. Okay, of course we don't have to write the dx using the tabular method. All right, so on the left-hand side, I'm taking derivatives. That's what we do to the u's. So the derivative of cosine of 4x will be negative sine of 4x, and then we have to multiply by the derivative of 4x, which is 4. Okay, then over here we're going to take an antiderivative, and we'll end up with sine of 4x. Okay, but if we took the derivative of this, by the chain rule, we'd get an extra 4, so we have to divide by 4 to compensate. Okay, now, our trick at this point is that we are going to move this sign across the table, right? We're going to realign everything. So if I move this across, and we use the box, is what's called the box method in one of the other videos. Note, of course, when you're doing integration by parts, right? Let's write the formula again quickly. At each step when you do the integral, you're just multiplying these things together. And if you want to do integration by parts again, you can break them up in any way you like, as long as the product doesn't change. So what I'm going to do here is take this 1/4 and slide it across, and negative 4 times 1/4 will just be negative 1. And this sine of 4x, I'm going to slide that across. So I'll get sine squared of 4x. Okay, but note here, I'm not actually integrating, I'm not differentiating. This is not an integration by parts step. This is simply reassigning the u and the dv. Okay, so the product, if you multiply across here, it has not changed. Okay, but now I'm going to go one more step in this way. So the negative 1's not going to change, but I want to use the identity cosine squared plus sine squared is equal to 1. Okay, here our angle is 4x. So if you have sine squared, this is the same as 1 minus cosine squared. So I can replace sine squared of 4x with 1 minus cosine squared of 4x. Okay, again, I have not actually done an integration by parts step. I'm simply rewriting the integrand. Okay, now I'm going to do an integration by parts step. So I'll take a derivative on the left, and that'll give me 0. And I'll take an antiderivative on the right, and that will give me x minus, well, I have an antiderivative of cosine squared of 4x. Okay? And so what we get is, okay, so we're going to do this multiplication step. Now inside the box, we were not doing integration by parts, so we're not doing integration. But I do when I leave the box, right? This was an actual step. So I multiply with a plus the first time, and then the next time you get a minus because of that minus. Okay, so let's see what we get. We have our original antiderivative, cosine squared 4x dx, and what does it equal? It equals, okay, we have a 4th times the sine and the cosine of 4x. So sine of 4x times the cosine of 4x. All right, now we have minus negative 1 times x, so that'll be plus x. We also have minus negative 1 times negative, and then we have this antiderivative. So that's 1, 2, 3 minuses. So minus, again, I have the antiderivative, 4x. Okay, so I've rewritten my original antiderivative in terms of another function that has another copy of this antiderivative. Well, let me add it to both sides. So now I get 2 times the antiderivative is going to equal a 4th sine of 4x cosine of 4x plus x. And if I want just this antiderivative, all I have to do is divide by 2 at this point. So this tells me that the antiderivative I'm looking for is equal to 1/8 sine of 4x cosine of 4x plus 1/2 x. Okay, so that's how we can do it without knowing sort of this trig identity, right? That sometimes is hard to remember. Okay, but of course this is a very nice way to do it. So I'm not telling you one way is right, one way is wrong. Okay, let's see. did this match, by the way, what we had? Well, it actually looks a little bit different here, right? Okay, we had the 1/2 x. Okay, there's the 1/2 x. But what we had up above, right, was 1/16 sine of 8x. Right? Does that compare? Is this equal to 1/16 sine of 8x? And of course the answer is yes, because sine of 2 theta is twice the sine of theta times the cosine of theta. And so if you have the sine of 8x, this would be the same thing as twice the sine of 4x times the cosine of 4x. Okay, so if we pulled a 2 out, this 1/16 would then become the 1/8. Okay, cool. So we didn't get something different. All right, what's next? This is a partial fractions situation. So let's do that down below. So we have, we're trying to find an antiderivative of 8 over x minus 1 times x plus 2. So we want to break up this fraction as two different fractions. So one of them is going to be over x minus 1. The other will be over x plus 2. And these a and b's are both constants. So if we multiply through by the denominator on the left, we're going to have 8 is equal to a times x plus 2 plus b times x minus 1. And now if I make x equal to -2, right, which, okay, remember, we're not really making it equal to it. We're actually taking a limit as x approaches it. But okay, we could basically treat it in this case like we're setting it equal to -2. We would have 8 is equal to, okay, well, this first piece goes away, and we would have b times -2 minus 1. Okay, so this is -3, and so b is going to equal -8/3. And similarly, if we let x be positive 1, then we'll have 8 is equal to a times 1 plus 2, and then the second sum end is going to be annihilated. That's a 3, and so a is equal to positive 8/3. Okay, so we can go back up here, replace our a with 8/3, and our b with -8/3. And so computing this antiderivative is now going to be very straightforward. We're going to get 8/3, the natural log, absolute value of x minus 1. Okay, we could check this by taking a derivative. And the only interesting part is we would have to use the chain rule, but the derivative of x minus 1 is 1, so nothing interesting happens. Okay, and then the second piece will be -8/3 times the natural log of the absolute value of x plus 2. Okay, so we can bring that back up. So the next piece will be plus 8/3 natural log absolute value of x minus 1 minus 8/3 natural log absolute value of x plus 2. Okay, finally we have this piece, and one might be tempted to say, hey, it's just like the second sum end, right? So you should just guess a natural log of 1 plus x squared. Okay, maybe you multiply by a 5. But this would be a mistake. Here you are not composing with a linear function like you were here. So when you take the derivative to check, you're going to multiply by a 2x. That ain't going to work. You can't just compensate by dividing by 2x, right? It does not work. No, in fact, you need to recognize, okay, ignore the 5, that this 1 over 1 plus x squared is just the derivative of the arctangent function. So this is going to be 5 times the arctangent function of x. All right, lots going on there. Hopefully this didn't go on too long for you.